Hello viewers, we're taking you through the story for A-Level Physics Paper 2. And this video we're going to go through the topic of waves in pipes and strings. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. Before we proceed, let's first look at the course outline of Physics Paper 2. So Physics Part 2 is divided into 4 parts. The first part is Geometrical Optics, where 2 questions come from these topics. And the second part is Physical Optics, where 2 questions come from these topics. The third part is Electrostatics and Electricity, where 3 questions come from these topics. And the fourth part is Magnetism and SC, where 3 questions come from these topics. So we are done with the part of geometrical optics and the part of electrostatics and electricity, and now we are on the part of physical optics. So physical optics, the first part of wave motion and sound transmission, calculations can be divided into 4 subtopics. The first topic is progressive and stationary waves, which I've already covered. And next part is waves in pipes and strings, which we are going to cover in this video. And after this, the third video will have Doppler effect, and the fourth one will have beats. And that will be the first part. Then we shall go to the second part, which is wavefronts and their properties. So here we're interested in the calculations, but complete notes and worked examples and try questions of all the topics of Physics Paper 2 are available in this book called Mastering A-Level Physics Paper 2 Edition 2023. So that is the current edition, which has been updated. And if you need a copy, contact the author on any of these 2 contacts. But a complete set of physics has 3 books. That is Physics Paper 1, Physics Paper 2, and a topical question bank. Principal Mathematics, there are also 3 books: Math Paper 1, Math Paper 2, and a topical question bank. Then subsidiary math, it is only 1 book, and the rest are for O-level. So for any of the copies, contact the author on those contacts. So now we shall start our topic of waves in pipes and strings. So this is also divided into 2 parts. There is waves in pipes and waves in strings. So now we are dealing with waves in pipes first, and that can also be called longitudinal stationary waves. So there are some terms which will be used in the whole of this video, and we need them, and we need to be aware of them. One is called fundamental frequency. So fundamental frequency is the lowest frequency. So sometimes they may not use the word fundamental, they just say find the lowest frequency. Always remember that when they talk about lowest frequency, it is the same as fundamental frequency. So it is the lowest frequency that a vibrating string or air in a pipe can produce. That is fundamental. The next term is called harmonics. So a harmonic is a note whose frequency is an integral multiple. So there are no fractions, it is just integers, integral multiple of the fundamental frequency of a particular instrument. Instrument can mean string or pipe. So if a fundamental frequency is F0, it implies that the harmonics have frequencies NF0, where n is an integer. So n can be 1, 2, 3, and so on. So that implies that when n is 1, that is called the first harmonic. When n is 2, we get the second harmonic. And when n is 3, we get the third harmonic, and so on. So that's what they mean by harmonics. It must be an integral multiple. The another term is called overtones. So an overtone is the frequency other than the fundamental frequency that is produced by a vibrating body. So here, if you realize for harmonics, when n was 1, we got f naught and we called it a harmonic. When n was 2, we got the second harmonic, 2f naught, and when n was 3, we got 3f naught. So for harmonics, even the fundamental frequency is included. But for overtones, you exclude this. And that means that now this will be the first overtone. When it comes to harmonics, this one is the second harmonic. But when it comes to overtones, it is the first, because for harmonics, we are not interested in the fundamental frequency. So that is the difference between harmonics and overtones. So now we shall go to what we call closed pipes. So pipes are of two forms. A pipe can be closed at one end, or it can be open at both ends. We shall look at both cases. So let's begin with what we call closed pipes. So a closed pipe is one in which one end of the pipe is open and the other end is closed. An example is a flute. So that means that when a blast of air is blown into the pipe at the open end, a wave travels towards the closed end so that a stationary wave is formed. So by now we know what a stationary wave is, because like I told you, stationary waves will be used more frequently in this video of waves in pipes and strings. With the node at the closed end, so I believe by now you know what a node is, and the antinode at the open end. So open, when it comes to a closed pipe, a node is at the closed end and the antinode is at the open end. So I shall draw diagrams to show you that, but for now that's what you need to know. Node is at the closed end, antinode is at the open end. So vibration modes in closed pipes. So vibration modes will deal with the three definitions of sine: fundamental frequency, overtones, and harmonics. So let's start with fundamental note or fundamental frequency. So this note produces the lowest frequency. So always when you hear the word lowest frequency, just know that it's a fundamental note. Lowest frequency and is known as the fundamental frequency. So let's try to illustrate. So that will be a closed pipe of length L, and the wave will be of that form, which is a stationary wave. I think realize that the node is at the closed end and the antinode is at the open end. So always closed pipes, node is at the closed end, antinode is at the open end. So when they talk about lowest frequency, this will be the shape. It will only have a quarter wavelength. So the length of the pipe will be equal to a quarter of the wavelength of the stationary wave. This is what I've been meaning. This L is equal to a quarter of the wavelength, meaning that wavelength is 4L. Therefore, fundamental frequency is given by V over lambda, where lambda is 4L. So this will be the formula for fundamental frequency. So when they ask for fundamental frequency and they have given you the length of the closed pipe, just know that fundamental frequency is V over 4L. So that is what they mean by a mode. So this one, the mode is called a fundamental note. or we can call it a first harmonic. So when they tell you to determine the mode of the lowest frequency, just say that the mode is a first harmonic. Then 2, part B, we have a mode which is called a first overtone. So we shall make a sketch. So first overtoned means that the wave is in that form. Remember, we said an antinode, a node must be at the closed end. So here the first node was here. Therefore the wave cannot stop here, because here it means that the closed end will have an antinode. Therefore it has to continue so that to the next node. So the next node produces this first overtone, and the next node produces the second overtone, and so on. So the first node produced the fundamental frequency, next node produces the first overtone, and the next node after that will produce the second overtone, and so on. So in this case, the length is equal to 3/4. Remember, from here to here is a half of the wavelength, and from here to here is a quarter of the wavelength. So a half plus a quarter gives you 3/4, which is this. So in that case, wavelength is equal to 4L/3. Therefore, the frequency of the first overtone is given by this expression, V/lambda, and lambda is 4L/3. We're going to substitute to get this. And when I try to rearrange to express it in terms of F0, I'll pull out this one, V/4L, which is F0, to come up with 3F0. This 3F0 means that the first overtone is equal to the third harmonic. I think remember the definition for harmonic, it is NF0. NF0. So now that we have 3, it means it is the third harmonic. So this knowledge is vital. Closed pipe, first overtone is third harmonic, because it will be used when we begin the calculations, as we will see. Then the second overtone, we shall have a pipe still of length L, but now to produce another node. So here, this one produced the first fundamental note, first overtone. Now this one has produced the second overtone. And the length now is equal to, from here to here, remember it is a wavelength, full wavelength, then plus a quarter. So 1 plus a quarter gives you 5/4. That's why you see a 5/4. That implies that wavelength will be equal to 4L/5. Therefore, the frequency of the second overtone is given by V/lambda. Substitute for lambda to give you this. Then remember that this one is equal to F0. So if I express in terms of F0, I'll come up with 5F0. Meaning, second overtone is equal to the 5th harmonic. So what can we conclude from that? We conclude that a closed pipe produces only odd harmonics. Remember, the first one was F0, second one was 3F0, and the third one was 5F0. So fundamental frequency N equal to 1, first overtone N equal to 3, second overtone N equal to 5. Meaning you can even know this third overtone, it will be N equal to 7, and so on. So that means that closed pipes produces only odd harmonics. So this information is also vital. We shall be using it. So whatever theory we are putting here is vital. It will help us in the calculations. There's no reason why we shall we just jump into the calculation without knowing some theory. However, it should be noted that the theory I put on this platform is not a complete and is not the complete notes you need to read. You'll need to buy the books I've recommended, because it is from those books that I pick out the theory I put on this platform. So that was about closed pipes. So we have got a conclusion that closed pipes produce only odd harmonics. Now the question is, what about open pipes? So for open pipes, when air is blown into an open pipe, a wave M travels to the open end Q. Remember, open pipe has two open ends. So when you blow here, the wave travels to the other open end. When you blow here, the wave travels to the other open end. That's what I'm meaning here. So there are two waves. The wave M travels to the open end Q, where it is reflected in the direction N on encountering the free air. So let's try to illustrate that. So that is our open pipe. So wave M is there and to be reflected back on encountering the free air. So that will be the format of the waveform stationary wave in an open end. Remember, for closed end, for a closed pipe, a node was at the closed end and an antinode at the open end. But now here we have two open ends, meaning that both open ends must have antinodes. That is why here there is an antinode here and also an antinode there. So a stationary wave is hence set up in the air in the pipe with antinodes at both ends. So that's what you need to remember, that for open pipes, antinodes are at both ends. Okay, so now we shall go through the vibration modes. Vibration modes are the same. We need the fundamental note, first overtone and second overtone. Then from there we shall make a conclusion. So let's start with the fundamental note. So this note produces the lowest frequency, known as the fundamental frequency. And the wave is in that form. So we shall have an open pipe. Then we shall draw our wave. So antinodes at both ends. So in this case, the length is equal to half the wavelength, because from here up to here is a quarter. Then also from here up to here is a quarter to give you a half. Therefore, when I make lambda the subject, it gives you lambda equal to 2L. The fundamental note is equal to V over lambda, and lambda is 2L to give you this. Remember, for closed pipe, here it was 4L, but now for open pipe, here it is 2L. So you should know the difference. So this means that the fundamental note is equal to the first harmonic. Then for the first overtone, means that you have to go to the next antinode this side and next antinode this side. For example, so that means that it will be in this shape. So that antinode is there and antinode is also there. So in that case, what will be the distance? This length will be equal to what? It will be This is a quarter. From here, tier. From here, tier is a half. And from here, tier is a quarter. So a quarter plus a half plus a quarter, you use the calculator to give you 1. So that means that lambda is equal to L. Therefore, the frequency of the first overtone is given in this form, where there is lambda, you substitute for L to give you. But we want to express it in terms of F naught. That's why you put an innocent expression of 2 and 2, 2 up, 2 down, to give you 2 in brackets V over 2L, where 2L is F naught. So here you realize that the first overtone is the second harmonic. For closed pipes, the first overtone was the third harmonic, but here it is the second harmonic. Okay, let's go to the third one, and then you can make a conclusion. So for the second overtone, the wave, this open pipe is there. Then we shall draw our wave. Okay, so that means that now the wavelength from here, tier is a half, is a quarter. This is a quarter. Then from here, tier is 1 because it is a full wavelength. Then from here, tier is a quarter. So a quarter plus a quarter is a half. Then a half plus 1 is 3 over 2. 3 over 2, therefore L will be equal to 3 over 2, implying that lambda is equal to that. Therefore, frequency of the first overtone can be given in this form. Sorry, of the second overtone, which is 3F naught, meaning it is equal to the third harmonic. So the first one was F naught. Okay. Second one is 2F naught. Okay. The third one was 3 is 3F naught. So N is 1, N is 2, N is 3. What does that mean? It means that an open pipe produces all harmonics, because it produces the first harmonic, produces the second, it produces the third, and so on. Whereas for open pipes, it produces the first, then skipped the second, produced the third, skipped the fourth, produced the fifth harmonic. So that is the difference between open pipes and closed pipes. Closed pipes produce only odd harmonics, while open pipes produce all harmonics. And for that reason that the open pipes are preferred as musical instruments than closed pipes, so that all notes are available. Okay, so now we have seen the vibration modes of both closed and open pipes. But there's something we need to talk about before we go to the calculation, and that is called end error correction. Because the waves that have been drawn have been ideal, but there is always an end error correction. So an end error correction is the length added to that of the pipe at the open end to compensate for the extension of the vibrations into the air outside the pipe. So for us, we have considered that the wave must stop at exactly the open end, but that is ideal. But practically, the wave extends a little, so we need an end error correction to cater for that extra distance. So let's start with an open pipe. Sorry, for a closed pipe. For a closed pipe, this is how the wave will practically be. So practically, the wave will extend a little outside the end of the open pipe. So that extra distance is what we call the end error correction. So that means that the rest is the same, only that now here, instead of just saying L, we say L plus E, where E is this extra distance. So this one is vital because that is what we use in the calculations. In calculations, we have to cater for that end error correction, meaning that lambda will now be equal to 4 in brackets L plus E. And that means that even the expression for frequency changes. It was initially V over 4L, now it is V over 4 in brackets L plus E. So that is what happens for all the modes. But for the sake of you understanding what an end error correction is, we shall look at only the fundamental for closed and also for the open. So for the open pipe, illustration is that, and because for it is open at both ends, it means that end error will be at both ends of the pipe. So we have this end error correction and also this end error correction, meaning that total length will be L plus 2E. For closed pipe, it was L plus E, but here it is L plus 2E because end error is done at both sides of the open end. And from here to here is half the wavelength, so that's why you say the whole of this length is equal to half lambda, giving you lambda equal to that. Therefore, the fundamental note or fundamental frequency will be given by that. So in calculations, we always cater for the end error correction. Okay. Then another thing, you'll hear the word resonance. So resonance, what you should know that in pipes, resonance occurs at the nodes and a loud sound is heard at this point. So here they can just say a loud sound. Just know that when they talk about a loud sound, it means there is a node. Okay, so with that we shall go through the calculations. Question 1 says, came from U.A.C.E. 1993, paper 1, question 8D Roman 1, and says, a closed organ pipe is of length this. Calculate the frequency of the first harmonic. And they give you the end correction as this, and the velocity of sound in air as that. So here we shall say, for the first harmonic, or for the frequency of the first harmonic, the waveform is in that shape. Meaning that L plus E is equal to a quarter of the wavelength. Meaning wavelength is equal to that when I make it the subject. And now that I know wavelength, I can come and say the frequency which they want is equal to V over lambda, and substitute for lambda to give you this. Then you can now substitute in that formula. V was given 340, L is known, and end error correction is known. So that gives you the frequency they wanted. So now we shall go to question 2. Question 2 came from U.A.C.E. of 1996, part 2, question 3D Roman 2, and it says, a cylindrical pipe of length 29 centimeters is closed at one end. Okay. The air in the pipe resonates. Know this word, resonates, with a tuning fork of frequency 860 Hz. Sounding near the open end of the tube. Okay. Determine the mode of vibration and find the end correction. And we need the velocity of sound in air as 340. So determine the mode. They want you to find out which harmonic is it. So we know L is 29 centimeters, convert to meters. Fn, frequency of the nth harmonic, is 860, and velocity of sound in air is 340. So first of all, we know that nth harmonic is equal to n times f naught, where f naught is the fundamental frequency. Therefore, we shall come and substitute. I think remember for closed pipe, we saw that f naught is equal to v over 4L. So I'll come and substitute for f naught. Then I know that Fn is 860, N I don't know it is what I want to get, V is 340 and L is 0.9. So that means that I can make N the subject and it will be 2.93. I think you remember the caution I talked about harmonics is that it must be an integral multiple. That means that, so I shall come here and say that for a pipe closed at closed one end, it only has odd harmonics. So we have 2.93. This one is already after 1, meaning that the next will be 3. Therefore, the mode of vibration is a third harmonic. And that's what they wanted in part when they asked for the mode. So you can either say third harmonic or you say first overtone. And we're saying that because our n is equal to 3, it was 2.9, but remember it has to be an integer, so it is already after 1, so the next is 3. That is why we chose n equal to 3. Okay, so now that we have the mode, we can go to the next part. The next part is find the end correction. So there we need to make an illustration. So for the third harmonic, I think you remember we drew something of this form. So we shall come and redraw it. When they talk about third harmonic, the wave is of that form. I think you remember it. The only difference that now here for us to add on the end error correction. So this from here to here is a half wavelength, from here to here is a quarter, meaning it gives you 3/4. So L plus E is equal to 3/4 of the wavelength, meaning wavelength is that. And after knowing the wavelength, I can come and say that V is equal to F times wavelength. So come and substitute V, F, and wavelength. I only have E as the only unknown, so make it the subject. Take the whole of this side to come up with this, then take the 0.29 this side to come up with this as the end error correction. That was question 2. Question 3 came from UNEB of 2014 paper 2, question 3C Roman 2, and it says a tuning fork of 760 Hz is sounded near the open end of a closed pipe of length 40 centimeters. If air in the tube resonates with the tuning fork, determine the mode of vibration and the end correction. So some are similar to the one you have just done, but we shall do it for practice so that you can conceptualize the concepts. So you know that Fn is now 760, L is 40 centimeters, convert to meters, and V is 330. So you go through the same procedure. Fn is equal to F is equal to N F naught, then substitute for F naught, and then put the values. Fn is that, V is that, L is that. Then make N the subject. It is still a decimal, but we need a whole number. So we shall come and say that for closed pipes only have odd harmonics. Now for us we have got 3 point something. Let me see what we have got. For us I've got 3.68, meaning that this 3.68 is already after 3 and the next will be 5. So that means that we are going to take n equal to 5. And we shall say that the mode of vibration they want is a 5th harmonic. Or you can say second overtone. So that was part A. And then part B, they wanted you to get the end correction. End correction, you have to draw that 5th harmonic. So it is not a must for you to draw this diagram, but I'm drawing it for you to easily understand the calculation. Otherwise, if you're after mastering the calculation, you can even bypass this one, as long as you remember that for a fifth harmonic, the length will be equal to 5 times a quarter of wavelength. So fifth harmonic length plus end error correction is equal to 5 times a quarter of the wavelength. If you can remember this, it is okay to bypass this diagram, but it is still better to draw it. So make lambda the subject to come up with this. Therefore, I can come and say that V is equal to F lambda, then substitute for V, for F, and for lambda. Then look for ways of making E the subject, and it will be equal to that. And that's what they wanted. Then question 4 came from UNEB of paper 2, question 1C, and it says, a tube 1 meter long, closed at one end, has its lowest resonance frequency. That means that it has its F naught at 86.2 Hz. Okay. With a tube of identical dimensions but open at both ends, the first resonance occurs at 171 Hz. Okay. Calculate the speed of sound and the end error correction. So here you have the fundamental note for a closed pipe and fundamental note for an open pipe. So for a closed pipe, L is 1 and F fundamental note is 86.2. So the mode will be, like I told you, it's okay not to draw this diagram, provided you remember the relationship between the length and the wavelength. So in this case, the length for fundamental note, length is equal to a quarter of the wavelength. So L plus E is equal to a quarter of the wavelength. Make wavelength the subject to come up with that. Then you can come and say that, but V is equal to F lambda. So come and substitute V is equal to F, which we have here, and lambda is here. And this lambda, you know, L is 1 meter, so substitute for L and call it equation 1. That is for a closed pipe. What about for an open pipe? For an open pipe, still we shall come and draw. It is okay not to draw, but for me I have to draw so that everyone can follow. Okay, so here what you need to know is that from here T is a half, meaning that this length is equal to wavelength. Sorry, it's equal to a half wavelength, because this is a quarter, this is a quarter. So it will be equal to a half wavelength, meaning lambda is equal to that. So from V equal to Fy, I can get the value of V, substitute for F and for lambda. And this L is 1, so that is equation 2. So we have equation 1 and equation 2. Both are for expressions of V, so you can equate the two equations to come up with that, which is, now we have only one unknown. So shall look for making it the subject. 1 shall open brackets, 2 shall collect like terms and make A the subject. And that's what they wanted. Then here they said, capture the speed and the end error correction. So speed, you can either get it from equation 1 or equation 2. So from equation 1, I'll substitute for E and be able to get the speed they wanted. Then question 5 came from UNEB of 95, paper 2, question 3C, and it says, a glass tube open at the top is held vertically and filled with water. Okay. A tuning fork vibrating at 264 Hz is held above the tube and water is allowed to flow out slowly. Okay. The first resonance. First resonance means fundamental frequency. Occurs when the water level is this, when L is that. Okay, from the top. While the second resonance is now the first overtone. Okay, second resonance occurs when the level is this, from the top. Okay, find Roman 1, the speed of sound in the air column. Roman 2, the end correction. So we shall need an illustration. So we shall have a tube having water. Then we shall have to draw the wave. Remember, resonance occurs at the nodes. So this one gives the first resonance and this gives the second resonance. So first resonance length is that L1 plus E. Then second resonance length is that L2 plus E. So L1 plus E is equal to a quarter of the wavelength and L2 plus E is equal to 3/4 of the wavelength. That's what we need from this diagram. So we know frequency, we know L1, we know L2. So you come and say that L1 plus A plus E is equal to a quarter of the wavelength, while L2 plus E is equal to 3/4 of the wavelength, as we have seen here. So equation 2 minus equation 1, when I subtract, I'll come up with this minus this. Then this cancels with this. Then the whole of this minus the whole of this gives you a half lambda. Therefore, lambda can be got, lambda is equal to 2 in brackets L2 minus L1. L2 is that and L1 is that. So that's the value of wavelength. Then the speed is f lambda. So f is given and lambda we have got it, so we can get the speed. So that was Roman 1. What about Roman 2? Roman 2, they want the end correction. So end correction, you can get it from any of the two equations. So from equation 1, I can substitute for L1 and get lambda, then get the value of E. And that will be the end correction they wanted. So now we shall go to question 6, which came from UNEB 2013, paper 2, question 3C, and it says, a uniform tube 80 centimeters long is filled with water and a small loudspeaker connected to a signal generator is held over the open end of the tube. With the signal generator set at 600 Hz, the water level in the tube is lowered until resonance is first obtained. First means that is the first or fundamental frequency. Is first obtained when the length of the air column is 13. Okay. If the third resonance, that is the second overtone, is obtained when the air column is 69.8 centimeters long. Calculate Roman 1, the velocity of sound in air, and Roman 2, the fundamental frequency for the tube if it were open at both ends. So we know that total length of the tube is 80 centimeters, convert to meters. Then the frequency is 600. Then length L1 for the first resonance is 13 centimeters, convert to meters. Length for the third resonance is 69.8 centimeters, convert to meters. Okay, then we shall need to draw to make an illustration. Then shall put the waves. Okay. So this is the first resonance, second resonance, and third resonance. We are interested in the first resonance, that will be L1 plus E. Then also the third resonance, that will be L2 plus E. Okay. So the first resonance, it is a quarter wavelength. Second one is from here, T is 1. Then here is a quarter, that is 5/4 of the wavelength. So L1 plus E is 1/4 lambda. Then L2 plus E is 5/4 lambda. Those are two equations, so I have to solve them. So subtract 2 minus 1 gives you this, and this gives you L2 minus L1. This cancels. Then this minus this gives you lambda. Therefore, lambda can be got by subtracting the 2. L1 is that, L2 is that, L1 is that, to give you this as the wavelength. Then V is equal to Fy. So frequency, wavelength, to come up with that. That was Roman 1. What about Roman 2? Roman 2, they want the fundamental frequency of the tube if it were an open at both ends. So open pipe, what is the formula for fundamental frequency? That is what you need to remember. But before that, we need to get the end error correction. So end error correction, come and substitute from equation 1, get the value of E. So you come and say that if the tube were open at both ends, then L plus 2E will be equal to a half wavelength, which gives you this. And therefore lambda will be equal to, you come and substitute for L and for E to come up with this as the wavelength. Therefore fundamental frequency is V over lambda to give you this as the frequency they wanted. So we have been dealing with waves in pipes. Now we are going to waves in strings or wires. So it can also be called stationary transverse waves. So when a straight wire which is tightly stretched is plucked, progressive waves travel to both ends, which are fixed where they are refracted to meet the incident waves. In that case, a stationary transverse wave pattern is formed in the string or wire. So now here we have some laws. There are 3 laws. So laws of vibration of stretched strings. We shall look at them. One is that the frequency of a vibrating string is inversely proportional to the length, provided the tension and mass per unit length is kept constant. So frequency is inversely proportional to length. That is 1. 2 is that the frequency of a vibrating string is directly proportional to the square root of the tension in the string, provided length and mass per unit length is kept constant. So we have this expression: F is proportional to root T, where T is the tension. Then the third law states that the frequency of a vibrating string is inversely proportional to the square root of the mass per unit length. So it's given in this form. So this mu is what we call mass per unit length. Now the question is, what will happen if we combine these three laws? So when you combine, this is what will come up. We shall come up with. We shall come up with this 1 over L, and we shall come up with the square root of T over mu. Then put a constant of proportionality to come up with this expression. And we know that K is equal to a half experimentally. So that one we have to just know it. So when you substitute for K, we shall come up with this, and that will be the expression for frequency of a stretched string, which is vibrating. So now we shall go to modes of vibration of stretched strings. So we have the fundamental note. So if a string is plucked in the middle, the simplest mode of vibration is obtained, and this is the fundamental frequency. So you have two fixed points, then when you pluck we get this vibration. So you have a nodes at the end and antinode in the middle. That means that from here, this length is equal to half the wavelength, meaning wavelength is 2L. Therefore, substitute and get the fundamental frequency. So by comparison with this, so when I compare this with this, you realize that 2L is already here. So what is left here is V, and what is left here is square root of T over mu, meaning that V is equal to square root of T over mu. Now this expression is also vital. We shall use it more frequently. They can give you tension and mass per unit length, and they ask for velocity. So the overtones also have nodes at the fixed ends and an antinode in the middle as follows. So what you need to know is that for strings, nodes are always at the fixed ends. So we shall go the first overtone. So you should ensure that the nodes are at the fixed ends and the antinode is in the middle. So I think you realize that an antinode is here in the middle, and nodes is at the end here and also at the end here. So that gives the first overtone. So here, from here, T is half, 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 which is 3 over 2. Therefore, lambda is 2L over 3. Therefore, frequency of the first overtone will be given by V over lambda. Substitute for lambda to give you this. Now, this one alone is equal to F naught. So it implies that F1 is equal to 3F naught. Therefore, the first overtone is equal to the third harmonic. Okay, what about the second overtone? So second overtone, still you should ensure that the nodes are at the fixed ends and an antinode is in the middle. So we shall come to that. That is when it is plucked in the middle. Okay, so I think you realize that the node is here, and here the middle there is an antinode, and at the end there will also be a node. That is when it is plugged in the middle. So L is equal to 5 times a half wavelength, so half, 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 to give you 5 times half lambda. Therefore, the frequency of the second overtone will be given by this, which gives you the 5 F naught. So in conclusion, we shall conclude that when a string is plucked in the middle, the overtones produced are odd harmonics. So note the position of plucking is in the middle, because they can say plucked a quarter way. That is a different story, but here we have considered the case where it is plucked in the middle. So with that, we shall go through these questions. Question 1 came from U.A.C.E, 2012, paper 2, question 3C, and it says, a wire of length 50 centimeters, density 8 grams per centimeters cubed, is stretched between 2 points. If the wire is set to vibrate at a fundamental frequency of 15 Hz, calculate Roman 1, the velocity of the wave along the wire. Roman 2, the tension per area of cross-section of the wire. So we have L as that, and we have the density as that. We convert to kilograms per meter cubed. So for the fundamental frequency, the note is in that form. So the diagram, I told you it's okay not to draw it as long as you remember that length is equal to a half of the wavelength for fundamental frequency. So that means that L is equal to half wavelength, meaning that lambda is equal to 2L. Substitute for L to give you the wavelength which is there. So now that I have the wavelength, I can get the velocity. Frequency times wavelength gives you the velocity. Then Roman 2, they want the tension per unit area of cross-section. So there, we shall remember that V is equal to T over mu. Then square both sides, we come up with V squared is equal to T over mu. Then we know that this mass per unit area is the same as density times cross-section area. But they want tension over area, so take this one this side to come up with this, then substitute for this and for density to come up with this as the tension per unit area. Then question 2 came from U.A.C.E, 2008, paper 2, question 2D, and it says, a string of length 0.5 meters and mass 5 grams is stretched between 2 fixed points. If the tension in the string is 100 Newton, find the frequency of the second harmonic. So L is that, M is that, and T is that. So for the second harmonic, we shall have such a wave. Okay, therefore what we need to remember is that the length is equal to wavelength. So wavelength is equal to length, and mass per unit area is mass per unit length is mass over length, which is this, to give you kilograms per meter. Therefore velocity is square root of T over mu. Mu is here and T is here, so substitute to get the velocity, which is that. So they want the frequency, so frequency will be V over lambda to give you 200 Hz. Then question 3 came from U.A.C.E of 2015, paper 2, question 3D, and it says, a wire of length this and mass this is under tension of this, the wire is plucked such that it vibrates in its third harmonic. Calculate the frequency of the third harmonic. So we know L, we know M, we know T. Therefore, mu is M over L to give you this. Then V is square root of T over mu to give you this. Therefore, the third harmonic, the wave is in that form. Okay, that means that the length will be a half, which is 3 over 2 of lambda. Therefore, lambda can be got as 0.4. Then frequency, which they wanted, will be V over lambda to give you 750. Question 4 came from UNEB of 2017, paper 2, question 3C, and says, the mass of a vibrating length of a sonometer wire is this. A note of frequency 512 Hz is produced when the wire is sounding its second overtone. Okay. If the tension in the wire is 100 Newton, calculate the vibrating length of the wire. So that is what we have, F, M, and T. So for the second overtone, when the wire is plugged in the middle, the wave is in this form. Okay, so the length will be now, let me see, 1, 2, 3, 4, 5. It will be 5 half wavelengths, so it will be 5 over 2 lambda. Therefore, lambda will be 2L over 5. Therefore, from V equal to Fy, you remember that lambda is this and V is this. So I'm going to substitute for V and for lambda. Let's do that in the next slide. So substitute for V and for lambda. Then you square both sides to come up with that. Cross multiply. But remember that mu is equal to M over L. So substitute for mu. Then rearrange. Cause this one and this just with one of these to remain with L just. Therefore, when I make L the subject, I can come up with the value of L as that. And that's what they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on Doppler effect and its application. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.